multifractal spectrum of SLE.
All right, so the topic from I talk today is the Mosher multifractal spectrum of SLE. So I'm going to start by giving giving the definition of the multifractal spectrum and the integral mean spectrum, which is another related quantity which we also computed. Then I'm going to explain the proof of the upper bound for the multifractal spectrum, followed by the proof of the lower bound for the multifractal spectrum. And then at the end, if I have time, I'm going to give a little bit more of the details of the proof, because the discussion of the upper bound and the lower bound here will be will be just kind of a broad outline, and I'll try to fill in some more of the details later. And this is based on joint work with Jason Miller and Shin Sun, who are also from MIT. So to start off, suppose we have a simply connected domain D in the complex plane, and we have a conformal map phi from the unit disk into our domain D. So typically, D is going to be a fractal domain of some sort, and in this talk, it'll be a complementary connected component of an SLE curve. The multifractal spectrum of the domain D is a means of quantifying the behavior of the derivative of the conformal map phi and its inverse near the boundary of the disk and the boundary of the domain D. More precisely, we define this set theta tilde s of D for each real number s to be the set of x in the boundary of the disk with the property that the modulus of the derivative of our conformal map grows like epsilon to the negative s as we approach the point in the boundary of the domain. And then we let theta s of D be the image of theta tilde s of D under the map phi. So this theta tilde s of D is a subset of the boundary of D. So here's just a basic illustration of what's going on here. So we look at this point over here, which is close to x, and we look at how phi prime behaves as epsilon goes to 0, and so we're getting closer to x. Kind of intuitively speaking, the multifractal spectrum is kind of measuring how much phi distorts distances near x. So the bigger the value of s, the more phi is increasing distances when we're near the point x in the boundary of the disk. And then the multifractal spectrum is defined to be the function which gives for each real number s the Hausdorff dimensions of the sets theta tilde s of D and theta s of D. Actually, it can be shown using some basic complex analysis that these two sets are just empty when s is not between -1 and 1. So really, the multifractal spectrum is kind of just a function on the interval -1 to 1. And the multifractal spectrum is kind of interest in its own right because it's a sort of natural means of quantifying the behavior of the derivative of a conformal map from the disk to a fractal domain. But it's also related to a bunch of other quantities of interest, such as the harmonic measure spectrum of D, the integral mean spectrum of D, which I'll talk about in more detail in a moment, the Holder regularity of the conformal map phi, and the Hausdorff dimension of the boundary of D. So over the past 15 years or so, there's been several results which are related to the multifractal spectrum of complementary components of an SLE curve. So kind of the most basic result of this nature is the computation of the Hausdorff dimension of SLE by Beffera in 2008. Additionally, there's been a calculation of the optimal Holder exponent for a conformal map into a complementary component of an SLE curve, and for the SLE curve itself by Lawler and Wiklund, which built on works by Rodenstrom and by Lind. There's been non-rigorous, in regards to the multifractal spectrum itself, there's been non-rigorous predictions by Duplantier and others for the multifractal spectrum of SLE and for several related quantities. And kind of an interesting historical note is that these predictions are what originally led Duplantier to conjecture SLE duality, which is the statement that the outer boundary of an SLE kappa curve for kappa bigger than 4 locally looks like an SLE 16 over kappa curve. And this has since been rigorously established in various works by Duodot, Zan, and Miller and Sheffield. So the first rigorous calculation of an almost sure multifractal spectrum type quantity for SLE is the calculation of the tip multifractal spectrum by Lawler and Viklund in 2012. This is kind of similar to the regular multifractal spectrum, but instead of looking at the whole boundary of the domain, you just look at the behavior of your conformal map near the tip of the SLE curve. And then additionally, Belyaev and Smirnov computed the average integral mean spectrum of SLE in 2009, which I'll talk a little bit more about in a moment. And then very recently, just actually posted to the archive yesterday, was a result of Alberts, Viklund, and Binder, in which they computed a dimension spectrum for points where SLE hits the boundary. And then additionally, there'll be some talks later today which also discuss results which are relevant to the multifractal spectrum of SLE and various related quantities. So the main result of my talk is the following theorem. So suppose we have an SLE curve eta in a smoothly bounded domain D in the complex plane. We define these two numbers S minus and S plus. And then it's almost surely the case that for each positive real number T and each complementary connected component V of our SLE curve, the multifractal spectrum of V is given by this dimension for the subset of the boundary of the disk, and this dimension for the subset of the boundary of V, or equivalently the subset of the boundary of the curve, because points which are not on the curve are just on a smooth boundary segment of the domain, so don't affect the multifractal spectrum. And then it's almost surely the case for all other values of S, the sets are just empty. So here we have a graph of the multifractal spectrum for kappa equals 2. It looks pretty similar for other values of kappa. So as you can see, it's a concave function, and it vanishes outside this range. The value that we obtain agrees with the predictions of Duplantier from earlier papers. It's invariant under replacing kappa with 16 over kappa, which is what we would expect from SLE duality, because if we look at an SLE kappa with kappa greater than 4, the outer boundary is just looks like an SLE 16 over kappa, and so the multifractal spectrum should be the same as for SLE 16 over kappa. Additionally, the function xi of S, which gives the dimension of the subset of the curve, is maximized when S is equal to kappa over 4. And its value there is 1 plus kappa over 8. So this value is of interest because it gives us the dimension of the boundary of the domain, because it just says that every point of the domain has to have some kind of derivative behavior as we approach the boundary. And so we can say that because basically we get that on a set of full dimension, the derivative grows like epsilon to the negative kappa over 4, and gives us the dimension of the curve as well. So in addition to the multifractal spectrum of SLE, our proofs also yield a calculation of the almost sure integral mean spectrum of SLE, which is defined as follows. So if we have a simply connected domain D in the complex plane and a conformal map phi from the unit disk into D as before, the integral mean spectrum is defined to be the asymptotic behavior of the average of phi prime to the A as epsilon goes to 0 for a given choice, for a given real number A. So it's natural to think that this should be related to the multifractal spectrum, because this is kind of the average growth rate of the derivative of phi, whereas the multifractal spectrum gives the size of the set of points where it has a given growth rate. And this indeed turns out to be the case, because essentially the same estimates which yield the multifractal spectrum also allow us to compute the Amosher integral mean spectrum. And the integral mean spectrum is of interest because it's related to several conjectures in complex analysis regarding the growth rates of coefficients of conformal maps and the boundary behavior of conformal maps and so forth. However, it's usually very hard to compute the integral mean spectrum for deterministic domains. But on the other hand, it can be more tractable for random domains such as complements of SLE curves. And an example which illustrates this principle is a result of Belyaev and Smirnov, where they compute the average integral mean spectrum of SLE, which is defined in the same way as the ordinary integral mean spectrum, but with an expectation of the derivative of the conformal map instead of the derivative of the conformal map itself. So in our paper, we obtained the Amosher bulk integral mean spectrum of SLE, which is defined like the ordinary integral mean spectrum, but you remove small neighborhoods of the tip of the curve and the starting point of the curve, because the derivative around these 2 points can have kind of weird behavior, which is different from its behavior near the bulk at points kind of along the bulk of the curve. And so we kind of just remove those points so that we just have to worry about sort of generic points along the curve. And so we obtain the Amosher value of the integral mean spectrum at every point A, and it's given by this function here. This A minus and A plus are just two constants which depend on kappa and are defined by a pretty complicated looking formula which didn't fit on the slide. And here we have a graph of the Amosher bulk integral mean spectrum of SLE. Notice that it's linear outside this range from A minus to A plus. This is actually something which we know has to be true by a theorem of Makarov, which characterizes all of the possible integral mean spectrums of domains. And another interesting thing to note about this is that it's not the same as the average integral mean spectrum of SLE. The average integral mean spectrum is the same in this middle range, but it doesn't have these same two linear segments outside the middle range. The reason for this is that there's kind of rare events in the which almost surely don't occur in the limit, but can occur at finite scales. And the possibility of these rare events contributes to the average integral mean spectrum and causes its value to be, and kind of throws off its value from the actual Amosher integral mean spectrum when you're looking at an exponent, which is very far from 0. So those are that kind of gives you a basic idea of the quantities that we're interested in this talk. And now I'm going to talk about the proof of the upper bound for the multifractal spectrum and the integral mean spectrum. So here we're trying to obtain an upper bound for the Hausdorff dimensions of certain sets. So what we need to do is estimate the probability that a given point is contained in one of our sets. By SLE duality, remember that the outer boundary of an SLE kappa for kappa greater than 4 looks like an SLE 16 over kappa. So we can just restrict attention to the case when kappa is less than or equal to 4. And then by a change of coordinates, we can assume without loss of generality that we're just looking at a chordal SLE kappa from negative I to I in the unit disk, and that the complementary connected component that we're interested in is just the right side of the curve. And for the sake of concreteness, we're going to consider the conformal map psi, which takes the right complementary connected component of the curve into the unit disk and fixes negative I, and 1. This psi is going to be equal to the map phi inverse that was used in the to the inverse of the map phi, which was used in the definition of the multifractal spectrum. So here's an illustration. We've just got our domain D8 over here, and we're mapping it out to the disk and fixing negative I, and 1. And we're going to compute the, we're going to get an upper bound for the almost sure multifractal spectrum of this domain. So kind of the reason we want to use this setup and look at the curve grown for all time instead of just running the curve to a finite time is that when we do the 2-point estimate, we're going to want to grow our curve eta from 2 sides simultaneously. And so we want to be looking at the entire curve and not just the curve grown up to some finite time so that we have symmetry by reversibility of SLE. But I'll say a little bit more about that when I talk about the proof of the lower bound. So the basic outline of the proof of the upper bound is as follows. We're going to start by using some reverse SLE martingales to obtain point-wise derivative estimates for the finite time inverse maps. So here we're going to look at the inverse maps in the loaner chain for SLE, and we're going to obtain derivative estimates for these. And then from these estimates, we can just use the kind of the usual argument in Hausdorff dimension calculations to get an upper bound for the dimension of the subset of the curve, and an upper bound for the dimension of the subset of the boundary of the disk, and an upper bound for the integral mean spectrum. Then we still need to consider the upper bound for the dimension of the subset of the curve, and that's going to require a little bit more argument. First, we're going to use a change of variables to get estimates for the area of the set of points where the derivative of the conformal map has certain behavior. And then once we have area estimates, we can argue that the probability that the derivative has given behavior at a certain point doesn't depend too strongly on the point. So if you know the expected area of the set of points where it has given derivative behavior, then you can also say that you know the point-wise probability that it has given derivative behavior. And then once we have that estimate, then we get an upper bound for the dimension of the subset of the curve. So to start off, we need to consider something called reverse SLE kappa, which is defined via the reverse Loaner equation. This just looks like the ordinary Loaner equation, except you have a negative sign here. And a solution to this equation is a family of conformal maps which go from the upper half plane into the upper half plane minus a hull, where you've got for some growing family of hulls kt. And if we take our driving function ut here to be square root of kappa times the Brownian motion, we get what's called a reverse SLE kappa. And the main reason why this is interesting is that it turns out that if you look at gt minus ut in this setup, then these maps are going to have the same law as the time t-centered Loaner map of an ordinary SLE kappa, ordinary forward SLE kappa at each fixed time t. However, they don't have the whole collection of maps doesn't have the same law. It's just an inequality in law at each fixed time. So this is our setup. We just got this reverse SLE Loaner chain, which is going from the upper half plane to the complement of the curve. So if we have this Loaner chain, this reverse Loaner chain GT, then this function MT here is a martingale. Martingale was first introduced by Lawler in 2009, and it's kind of a reverse SLE analog of the Schramm-Wilson martingales for forward SLE, which were introduced in the paper SLE coordinate changes in 2004, 2005, something like that. So we can say exactly what law we get when we reweight by this martingale MT, and this is the curve whose law is equal to the law of the reverse SLE reweighted by this martingale is what's called an SLE kappa rho with a force point of weight rho at the point z. So this is kind of like an ordinary SLE, except that you keep track of this extra marked point z. And it has, it can have slightly different behavior because the force point can cause it to be pushed away or pulled towards the point z. And we're going to call this reweighted law p star z for a given point z. So if we look at a point z, which is very close to the boundary of the upper half plane, so its imaginary part is equal to epsilon, and it's not too close to either 0 or infinity, then just by rearranging the formula for this martingale and using the optional stopping theorem, we obtain that the probability that gt prime of z is of order epsilon to the negative s is approximately equal to epsilon to the alpha times the reweighted probability that gt prime is of order epsilon to the negative s, where this alpha here is just some constant which depends on rho. So here and throughout the rest of the talk, the squiggly equals sign will mean that the quantity is bounded between epsilon to the negative s plus u and epsilon to the negative s minus u, where u is some small but fixed parameter which we're eventually going to take to 0. So it's kind of an inequality modulo an O of 1 error in the exponent. So we claim that if we take rho equal to 4 plus kappa s over 1 plus s, then the reweighted probability that gt prime of z is of order epsilon to the negative s is proportional to 1. And so once we have this statement, then we get our desired pointwise derivative estimates, because then this just tells us that the probability, the unweighted probability that gt prime of z is of order epsilon to the negative s, and hence the unweighted probability that the inverse SLE maps for a forward loaner evolution are of order epsilon to the negative s is just going to be around equal to epsilon to the alpha, and this is the estimate that we want. So to show that the reweighted probability that gt prime is of order epsilon to the negative s is proportional to 1, we're going to use a coupling of reverse SLE with a Gaussian free field. So the way this works is that we apply a theorem of Sheffield, which says that we can find random distributions h and ht for each fixed time t, which are Gaussian free fields plus certain harmonic functions, with the property that h composed with gt plus this constant times log gt prime has the same law as ht under the reweighted law, where here q is just this constant which depends on kappa. So the picture looks kind of like this. We've got this conformal map, just taking our marked point z and kind of pulling it up the curve, and then this distribution over here, h follows gt plus q log gt prime, has the same law as this one over here. The way we get an estimate for gt prime out of this is that we estimate h follows gt and ht using circle averages, and then we just rearrange this equality to get that under the reweighted law, it's the case that gt prime of z is of order epsilon to the negative s with high probability, and that's what we want. So then this gives us our desired 1-point estimate for the reverse loaner maps. And actually we can do something a little bit better. So using some stochastic calculus and a symmetry result between forward and reverse SLE kappa rho, which was proven by Duplantier, Miller, and Sheffield in 2014, we can also add some extra regularity conditions to our lower bound. So instead of just saying that the derivative here is of order epsilon to the negative s, we can say the derivative is of order epsilon to the negative s, and the curve doesn't have pathological behavior. I'll explain exactly what the regularity conditions involved here are later in the talk, because they're kind of technical to state. But this is by far the hardest part of the 1-point estimate, getting these extra regularity conditions. But it's also kind of crucial that we have these later in the proof. This is also the main reason why we can't just use other kind of related results which give sort of similar looking estimates for the derivative of inverse SLE maps. For example, estimates by Rodenstrom and by Belyov and Smirnov, because these estimates don't have the regularity conditions that we need, and so we kind of have to go through, we kind of have to derive the estimates from scratch so that we can get the desired regularity conditions in the lower bound. So this gives us the upper bound. So this pointwise estimate gives us the upper bound for the dimension of theta tilde s of the question.
Yeah, I mean, just to understand correctly, so the extra regularity conditions are not used to prove the upper bound, but are used in order to prove the estimate that you will need in the input as in the upper bound, right? Is that the idea?
Right. So they're
in the lower bound.
Yeah, so they're not used to prove the estimates for the inverse maps and they're not used in the proof of the upper bound for the dimensions of theta tilde s of our set, but they are used in transferring the estimates for the inverse maps to estimates for the forward maps, and therefore in the proof of the upper bound on the dimension of the subset of the curve, and then they're also used in the proof of the lower bound for the dimension. Right, so once we have these pointwise derivative estimates for the inverse maps, we get upper bounds for the subset of the line in this case, because we switched to working on the upper half plane instead of the disk, and for the integral mean spectrum, and just by some basic complex analysis, we can transfer these to estimates for the domain d eta, which is a subset of the disk, which I introduced earlier. So next we need to consider the upper bound for the Hausdorff dimension of the subset of the curve, the set theta s of d eta. And so the way we do this is we start by using a change of variables in the Kolbe-Quarter theorem, which says that the derivative of a conformal map, here this ft is the forward-centered loaner maps. So here I'm switching from working with our reverse loaner chain to working with a forward loaner chain. And so I use the Kolbe-Quarter theorem and a change of variables to get that we can estimate the area, to get an estimate for the area of the set of points z in the upper half plane with the property that ft prime of z is of order epsilon to the s, and the distance from z to the curve is of order epsilon to the 1 minus s. So I can say that the expected area of the set of points with this property is of order epsilon to a certain power, which depends on s and kappa. So then we argue that the probability that a point satisfies these conditions, the probability that ft prime of z is of order epsilon to the s, and the distance from z to the curve is of order epsilon to the 1 minus s, does not depend too strongly on the point z. So this allows us to transfer the estimates for the expected area of our set to estimates for the probability that a given point satisfies these two conditions. And so here we get the probability that this point z is close to the curve, and that the derivative of this map here has the desired behavior is proportional to epsilon to a certain power, which depends on s and kappa. Right, and so then these estimates eventually give us the upper bound for the dimension of the subset of the curve. And so then this completes the proof of the upper bound for the integral mean spectrum. And now we turn our attention to the lower bound. So we're going to start by proving a lower bound for the subset of the curve. So this is the opposite direction as we did for the upper bound, where we started with an upper bound for the subset of the circle, and then we transferred to an upper bound for the dimension of the subset of the curve. Here we're going to start with the subset of the curve and later transfer to the subset of the circle. And the reason for this is that we want to use some stuff from Miller and Sheffield's imaginary geometry papers, which is much easier to apply if you're working with the geometric properties of the curve rather than with just with a conformal map. So to simplify notation, we're just going to define this parameter q to be s over 1 minus s. And the way we're going to prove a lower bound is by a more or less standard argument. So what we're going to do is we're going to define nested events, En of z, for each point z in the disk with the following properties. If En of z occurs for every n, then z is in our multifractal spectrum set. We can get an estimate for the probability of En of z for each integer n, and kind of most importantly, we have this estimate on the correlation between En of z and En of w in terms of the distance between z and w. So once we have these events, we can define a measure which is called a Frostman measure on a kind of carefully chosen subset of theta s of d eta, which is in some sense self-similar. And this set is called the perfect points. And so we get this Frostman measure, which is defined by the condition that the double integral over the set of 1 over absolute value z minus w to the alpha with respect to the measure is finite for any given alpha less than the dimension of less than the desired dimension for theta s of d eta. And then by some standard results about Hausdorff dimension, the existence of such a measure implies that the Hausdorff dimension is at least xi of s, and so that gives us our desired lower bound. So the difficulty in the proof is then constructing these events En of z with these three properties. So the way we construct the events is we're going to grow the curve eta from both directions, and we're going to kind of zoom in a bunch of times and define an event, a new event, which kind of looks the same as all of the previous scales each time we zoom in. So we let eta bar be the time reversal of our curve eta. So remember that eta is this SLE from negative I to I in the unit disk. And so eta bar is then an SLE from I to negative I by reversibility of SLE. And we're going to look at the behavior of our curves eta and eta bar at the first time they hit this small ball centered at a point z. So here's the picture. We grow eta and eta bar up until they hit this ball of radius e to the negative beta. Then we're going to apply a conformal map, which takes the complement of these two curves to the unit disk and fixes negative I, and 1. So this conformal map can kind of be seen as an approximation to the map psi that I talked about in the previous stage, which maps out the entire complement of the curve. So in order to define our desired events, we're gonna iterate this procedure. So we're going to define we define eta 0, 1 to just be the curve eta. Then inductively, if we've defined eta 0 j for some j, we define eta sub 0 j plus 1 to be the curve obtained by running eta 0 j in its time reversal up until the first time they hit the ball of radius e to the negative beta, and then mapping out the two sides of the curve, and then looking at the image of the middle part, which is going to have approximately the same law of eta, but the endpoints of the curve might be a little bit different. And the way that we deal with that is just by growing the curve just a little bit more until we can find a conformal map which takes the endpoints to negative I, and so that we get something that has exactly the same law as at the previous stage. So the setup looks like this. Here's our curves at stage j. We conformally map out these two black parts of the curve. And then we're in the setting of the disk, and we've got this SLE curve started from some pair of points, which are not necessarily equal to negative I and I. But then we grow out these little purple parts at the end and map them out as well. And then once we do that, if we kind of carefully choose the times that we're growing these purple curves up to, then we can end up with a curve which actually goes from negative I to I, and so has exactly the same law as our original curve eta. And then we call that curve eta 0 j plus 1. Yes?
Can you explain what
again?
Oh, this is just a conformal map which you look at the complement of the two black curves in this picture, and then you take that complement to the unit disk, and you fix 0 and have, say, positive real derivative at the origin.
And so then the tips of those two slits are going to the boundary.
Yes.
And then what's that little purple piece?
So the tips are going to the boundary, but they're going to points which are not necessarily equal to negative I and I. But I want to have a curve which has exactly the same law as my original curve that goes from negative I to I. So what I do is at each stage, I look at the conformal map which fixes 0 and has positive real derivative there. And that goes from the complement of these, like a little segment of this and a little segment of this, to the unit disk and fixes 0 and has positive real derivative there. And then I grow these curves up to a certain stopping time, which is going to be the first time that this conformal map actually takes the tips to negative I and I. And you can show that with positive probability, if you grow the curves in the right way, then the stopping time will actually be finite. And so you do get a stopping time where your tips are taken to negative I and I. And so then you can get a conformal map which fixes the origin and which also fixes negative I and I. And so you get exactly the right law. You can't just use such a map directly because you don't have enough degrees of freedom with choosing a conformal map, because you can only specify the image of one boundary point and one interior point, but we want to specify the images of two boundary points and interior point. So we have to kind of use this extra little trick. Then we define a map psi 0j in the same manner as the map phi beta above. So this is just the map from the complement of the curve, or the complement of the two sides of the curve, which fixes negative I and 1. And we let E sub 0j be the event that the derivative of this map at stage j, this is a typo, this should actually be phi sub 0j, is of order e to the negative beta q. And then plus a lot of regularity conditions. So then we define our events En at the point 0 to just be the intersection of the E0j's. And for a general point, we define it in the same way, except we first apply a conformal map, which takes z to 0. And then once we've applied the map, then we just define the events in exactly the same way as before. So then the perfect points are, roughly speaking, the set of points for which En of z occurs. And we want to show that these perfect points satisfy all of the those three conditions on the first slide. First of all, we can use the 1-point estimate. Let's say more on this in a second. We set up the events and define the regularity conditions on them in such a way that the intersection of these events En of z is contained in the event that z is in the set. So if En of z occurs for every stage, then z will be contained in the multifractal spectrum set. And then one can argue that the probability that this map phi beta is of order e to the negative beta q will be of approximately the same order as the probability that the map psi that we used in the upper bound that we used in the 1-point estimate is of order e to the negative beta q, and the distance from z to eta is of order e to the negative beta. And we know that probability by our 1-point estimate. And so then, because we have this Markov property at each scale, we can just multiply the probabilities, and we get the probability of En of z for each point is of order e to the negative n beta times gamma star of q, where this gamma star of q is just an exponent which depends on kappa and q, which, remember, q is just s over 1 minus s. So what remains to do is to check that we have this correlation estimate in terms of the distance from z to w. So we consider 2 points z and w whose distance is approximately e to the negative k beta for some fixed k. And we need to estimate the probability of En of z intersect En of w for n greater than or equal to k. and then this will lead to the desired estimate on the correlation between our events in terms of the distance between the points. So the idea here is that because we start at distance e to the negative k beta, once we apply our conformal map at stage k, then we're going to end up with points which are at constant order distance apart. So here we look at the stage k curve, and here they might be, they're going to be pretty close together here when we're at stage k. But then once we map out the two sides of this curve, we're going to end up with points which are at constant order distance apart from each other. And we'd like to say that the behavior of the derivatives near these 2 points are approximately independent. But unfortunately, this is not quite the case because we're interested in a conformal map, which depends on the whole curve. So little fluctuations in the curve near z could have an effect on the whole conformal map, and this could mess things up near w. So you don't get approximate independence just using this setup. So to get around this, we have to localize our events so that things really only depend on what happens near z and what happens near w. And this is where the imaginary geometry stuff comes in. So we can couple our curve eta with a Gaussian free field h with the property that eta is the flow line of h started from negative I in the sense of Miller and Sheffield's imaginary geometry papers. So then at each stage in the construction of our events, we're going to add auxiliary flow lines of this same field h started at the tip of the part of the curve that we've grown so far. So the picture is now going to look like this. We've got, instead of just running the curves up to the first time they hit this disk and then mapping out the two sides, what we're going to do is we run the curves up to the first time they hit the disk, and then we grow these extra green curves, which are going to be our auxiliary flow lines. So we call A to Z plus and A to Z minus. Started at this same point, and we run them up until the first time that they form a pocket around the point Z. And then we define our events instead of mapping out both sides of the curve, we just map out this green pocket, and we just look at what happens inside here. Then we do the same thing at the next stage, and then continue and do this at every subsequent stage. Right, so the pockets formed by these auxiliary flow lines have the property that if you condition on the pocket, then what happens inside is conditionally independent given the pocket from what happens outside. And so if we define everything so it only depends on what happens inside the pocket at the previous stage, then we get that when we look at the same picture as before, where we have these 2 points, z and w, at distance of order e to the negative beta k from each other. Then now when we map out the stuff happening at the next stage is going to depend only on what happens inside this pocket centered at z and inside this pocket centered at w. And we actually can say exactly that if you condition on these 2 pockets, then the stuff inside the pockets are conditionally independent. And so here we actually do get that what happens over here is independent from what happens over here. And then this gives us our desired correlation estimate for our events. And then hence we get using the usual Frostman measure argument, we get the lower bound for the dimension of theta s of d eta. So we get the lower bound for the dimension of the subset of the curve. And then we can use these same estimates and some more or less minor tricks to transfer these to lower bounds for the dimension of the subset of the circle and for the integral mean spectrum. So this concludes the proof of the outline of the proof of the almost sure multifractal spectrum. So I guess since I started 10 minutes late, I'll talk for a few minutes about some of the many details of the proof, which I kind of just ignored during the previous outline. So first I'll say a little bit about what the regularity conditions on all of these events actually are. So the kind of have two more or less equivalent regularity conditions, which are sort of the main, most important regularity conditions and are on virtually every event in this paper. So the way we define these is, suppose we have a closed set in the unit disk, which we'll call A. So typically A will be some part of an SLE curve. And we let D be a complementary connected component of A, and let F be a conformal map from D to the unit disk, and we let mu be an increasing function. And then we define two events which depend on these inputs. So first is the event script G of F mu, which roughly speaking is the event that if we've got 2 points x and y which are sufficiently far apart, then F does not map these 2 points too close together. Hence the name reverse continuity condition. It's saying that, if two things are not too close together, then their images are not too close together, which is kind of like the dual notion of continuity in some sense. And then second, we define this event script G prime of A and mu to be the event that A doesn't get too close to the boundary of the disk without actually intersecting the boundary of the disk. So here's a picture. The event script G of F mu will tell us that if we take 2 points, say these ones here, and we know that this red arc between them is not too short, then their images are not mapped to things which are really close together. And then the event script G prime tells us that say this curve, this set A here, which I've drawn as a curve because typically it will be a curve in our applications, say that it doesn't get really close to the boundary here without actually intersecting the boundary. So I said that these two events are equivalent in the sense in which that's true is as follows. If we're given any mu, then we can find a mu prime, which depends only on mu, with the property that script G of F mu implies script G prime of A mu prime for any choice of A. And also vice versa, we can find given a mu, we can find a mu prime such that script G prime of mu implies, or script G prime of mu implies script G of mu. So the kind of the intuitive reason why this is true is, suppose we're in this picture and we look at a Brownian motion started from say this point. Okay. So if this curve gets really close to the boundary without hitting it, then it's very unlikely that a Brownian motion started over here is actually going to make it over to this red arc without hitting A. And so one can use conformal invariance of harmonic measure to say that if this curve is getting really close to the boundary, it's unlikely that your Brownian motion makes it over to the red arc, and hence the image of the red arc will be very small, and hence the event script G will fail if script G prime fails. And then that proves the contrapositive of the desired equivalence in one direction, and the other direction is treated similarly. So I guess why are we interested in these kind of weird-looking regularity conditions? Well, first, script G is useful because remember that we were normalizing all of these conformal maps so that they fix negative I, and 1. So when we're working with maps which fix negative I, and 1, and we want to get a new map which fixes negative I, and 1 after we apply some transformations of things, we need to apply a Mobius transformation which takes the images of negative I, and 1 back to where they're supposed to be. And we don't want this Mobius transformation to distort things too much, because then this will mess up our derivative estimates. And this is basically equivalent to saying that the images of negative I, and 1 are not too close together. Because so long as the images of the points that you're mapping to negative I, and 1 are not too close together, then your Mobius transformation isn't going to distort distances and derivatives and such too much, and hence you get and and this is exactly what the event script G is telling us, that the points won't be mapped too close together. And then the condition script G prime is important because a lot of our estimates are degenerate near the boundary of the domain, and so we want to keep stuff away from the boundary. And then the fact that these two events are equivalent is also extremely useful because script G behaves nicely under composition of maps. If we compose two maps and they both satisfy this script G condition, then the composition will also with a function which depends only on the mu's for the two original functions. And on the other hand, the event script G prime is nice to deal with geometrically. And so this equivalence of these two events allows you to transfer geometric information into information about the conformal maps and vice versa, which is extremely useful in dealing with all of these estimates. The other question? Right, so then another detail which I've kind of swept under the rug throughout this is that when we do the 2-point estimate, we look at these pockets. When we condition on the pocket, the part of the curve inside the pocket is not actually an SLE. It's an SLE kappa rho L rho R for two force points rho L and rho R. But we can deal with this issue as follows. So remember in the earlier slide where I was growing those two little parts of the curve, the little purple parts of the curve at either end, and then mapping those out. This kind of serves a secondary purpose in addition to moving the tips back to -I and 1, which is where we want them to be. It also moves everything away from the boundary. And once you have it, you can show that once you have if you have an SLE kappa rho, and then you grow the two sides up until and you grow it from both ends and get it away from the boundary, then the stuff that you have in the middle after you map out these two purple sides is going to be strictly mutually absolutely continuous with respect to the law of an ordinary SLE kappa, which means that it's mutually absolutely continuous and the radon-Nikodym derivative is bounded above and below by deterministic constants. So basically what happens is, kind of in this picture, you have this pocket, you map out the pocket, you get an SLE kappa rho, and then you grow from both sides and you get, and you map out the two purple sides, and then you get something which is very close to being an SLE kappa in a very precise sense. And so this is how we deal with this issue of not actually having SLE kappas at each stage. And then I guess I'll just say a little bit more about one last issue in the proof, which is remember that the squiggly equal sign means that we have an estimate up to an O(1) error. So we need to deal with these eventually because we want to have an exact limit in the definition of our multifractal spectrum sets. So we have to let U go to 0. But the constants and all the estimates degenerate when U goes to 0. So we have to also let beta go to infinity at the same time to counteract that. So what really happens is that in the definition of the nth event, we don't really have a beta at each stage. What we have is a beta n, which grows at approximately a logarithmic rate as n goes to infinity. So at each stage, you're not growing up to the first time they hit a ball of fixed size. The ball gets a little bit smaller at each stage of the construction. So then I just wanted to mention a couple of kind of related directions that one can take after this work. So there's something called the winding spectrum of SLE, in which one studies the asymptotics of the argument of phi prime rather than the asymptotics of its modulus. And you can also consider something called the mixed spectrum, where you consider the argument of the modulus at the same time. This winding spectrum and mixed spectrum have also been predicted by Duplantier and Binder in various papers. And actually, an upper bound for the winding spectrum was proven by Aru, who's going to give the next talk today. And then additionally, one can try to look at the multifractal spectrum of SLE kappa rho near the points where it intersects the boundary. So all of our stuff applies for SLE kappa rho when you restrict the subsets of the curve away from the boundary just by various absolute continuity arguments. But if you want to look at like what happens near the boundary, some additional stuff is necessary. This is the same as, so it's the same as for ordinary SLE away from the boundary, but there's issues near the boundary. And maybe this could be done using techniques similar to those of our paper, or maybe the recent paper by Alberts, Binder, and Viklund. So that's it. Here's the references I cited during the talk.
You say that the spectrum you're investigating is closely related to the harmonic measure spectrum?
Yes.
How is the relation?
So it's actually equivalent to knowing the harmonic measure spectrum. One can show that if you look at the set of points where the harmonic measure of the epsilon ball centered at the point grows like a given power of epsilon, and say that it grows like epsilon to the r, look at that set, then I believe that that set will be exactly the same as a multifractal spectrum set with r equals 1 over 1 minus s. So they're just equivalent. The multifractal spectrum was just nicer to deal with, nicer to actually compute with, because it's kind of defined in terms of derivatives rather than harmonic measure. Yes?
So a question concerning the integral mean spectrum. We focus at the point -2. Which value of kappa maximizes the integral mean spectrum of that?
I'm not sure off the top of my head, but you can plug it into the formula and see what.
Maximizes everything. Four maximizes everything.
Okay. Yeah, 30, so it would be 4.
If not, let's think again.